In this session, I want to go back and finish simultaneous equations on graphs, the section that we did in a previous session that we didn't quite finish off. So I just want to go back to this section, finish off these few questions here, and then if I get time, I'll move on to quadratic inequalities. So remember what we were saying about simultaneous equations on graphs. Basically, we were solving simultaneous equations algebraically, and then we looked at some examples where we graphed two straight lines, and where they intersect was the solution to those simultaneous equations. And then we graphed also a quadratic in a straight line and said where they intersect, there's the two solutions of those. Also, we said that a quadratic and a linear equation can have two solutions, one solution or no solutions. And that's about where we got to, and I didn't quite finish off these questions, so that's what I'm going to be doing today. So starting on question 7 then. It says determine the number of points of intersection for these pairs of simultaneous equations. So A, we have y equal to 6x squared plus 3x take 7, and y equal to 2x plus 8. And we start this off algebraically. Excuse me. We start this off algebraically. As we usually do, we substitute the linear equation into the quadratic. So y equals 2x plus 8, so substitute that into the first equation here. We would get y equal to 6 multiplied by 2x plus 8 plus 3 times sorry, I've done it the wrong way around, haven't I? 2x plus 8 is equal to all of this, 6x squared plus 3x take 7, and then we simplify it. No, actually, I'm late. I've just started. I'm very late today. I'm trying to start these at 11 AM every day, but today we are starting much later. And then we simplify. So I'll actually take that 2x from the left hand side, subtract the 8, we'll end up with 6x squared plus x take 15 equal to 0. And then we could, if it looks easy to factorize, we could actually factorize, but you don't really need to factorize, you just need to look at the discriminant. So remember, the discriminant is b squared take 4ac. That's that part under the square root in the quadratic equation. And then we find whether this is greater than 0, less than 0, or equal to 0. So the b is 1 take 4 times 6 multiplied by c, which is negative 15. And well, this is clearly greater than 0. I guess we should probably compute it, but you don't even really need to figure it out if you can just see that it's greater than 0. But let's go ahead and do it anyway. So this is going to be 24 multiplied by 15 plus 1, so 361. And then we can say, therefore b squared take 4ac is greater than 0. Remember what that means? That means the quadratic has two solutions. Therefore, this set of simultaneous equations has two solutions. And remember, all the question is asking is determine the number of points of intersection. So if it has two solutions, there will be 2 points of intersection. So therefore, they will have 2 points of intersection. Okay. And yeah, the next two will be similar to that. Basically, started off algebraically, get your quadratic in terms of x. Sometimes it might be in terms of y, either way. And then find your discriminant to see how many points of intersection there will be. Okay, moving on to question 8 then. Question 8 says, given the simultaneous equations, 2x take y equal to 1 and x squared plus 4ky plus 5k equal to 0, where k is a non-zero constant, show that x squared plus 8kx plus k equals 0. And that's it for part A. So we can substitute the first equation into the second equation as we usually do. So rearranging this first, for y we would have y equal to 2x take 1, and then sub that in here, we would get x squared plus 4k multiplied by 2x take 1, substituting that for y there, plus 5k equal to 0. And simplifying further, expanding those brackets out, we get x squared plus 8kx take 4k plus 5k equal to 0. And then x squared plus 8kx plus k equal to 0. And we've shown that's the case for part A. Part B says, given that x squared plus 8kx plus k equals 0 has equal roots, find the value of k. Okay. Well, if this has equal roots, that means the discriminant is equal to 0. B is 8k, so we have 8k all squared, take 4 times 1 multiplied by k equal to 0. 8k squared is 64k squared, take 4k equal to 0. Divide through by 4, we get 16k squared, take k equal to 0. And solving for k, you could factorize a k from both terms. Then we get k multiplied by 16k take 1 equal to 0. So k is equal to 0, or k is equal to 1/16. But remember, in the question it tells us k is a non-zero constant, so this solution is invalid. Therefore we can say k is equal to 1/16. And then for C, it says, for this value of k, find the solution of the simultaneous equations. Going back to the original equations, remember we had a k in that quadratic, so we plug that in. Sorry, we'd plug it in here to the equation in part A. That's the quadratic we got where the graphs intersect. That will give us the solution. So plugging k into this equation here, we get x squared plus 8 multiplied by 1/16 x plus 1/16 equal to 0, and then x squared plus a half x plus the 16th equal to 0. And maybe you can see that we can actually factorize this. It's a bit of a funny one because we have two fractions, but maybe you can see the factors of 1/16 that make a half. This would be x plus a quarter multiplied by x plus a quarter. You're a bit late, actually. You can wait outside, thank you. I'll have a chat to you in a minute. So x is equal to negative a quarter. remember, we're assuming there is equal roots, so we're always going to get one solution here. And then if x equals -1/4, remember y equals 2x take 1, so y is going to equal 2 multiplied by -1/4 take 1, and this is -1/2 take 1. This is -1/2 or -3/2. Okay, and that was part C. And I'll check all of these in a minute. I just want to finish off question 9. Question 9 says a swimmer dives into a pool. Her position p meters underwater can be modeled in relation to her horizontal distance x meters from the point she entered the water as a quadratic equation. P equals half x squared take 3x. The position of the bottom of the pool can be modeled by the linear equation p equals 0.3x take 6. Determine whether this model predicts that the swimmer will touch the bottom of the pool. This is introducing context into so far what we've just been doing, purely mathematically. So we have a pool here. We could do a quick sketch even. And the depth of the pool, or the distance under the surface of the water, is modeled by p, and the distance from the start of the pool is x. And well, the bottom of the pool would look something like this. Now it wouldn't be exactly modeled by a straight line, because I doubt you'd have swimming pools like this, right? You wouldn't have a triangular swimming pool of it. You'd have like some curve there, right? But it's an approximation, as all mathematical models usually are. So the bottom of the pool is that straight line. We have the dive of the swimmer, and that's approximated by a quadratic equation, as they tell us. So that's going to look something like this, right? As a dive usually looks, you go down and then up again. Now the question is, will she hit the bottom of the pool or not? So we can solve these two equations to figure that out. So p is equal to a half x squared take 3x, and the bottom of the pool is equal to 0.3x take 6. And let's go ahead and solve these as we normally would with simultaneous equations. So if p equals 0.3x take 6, let that equal to this quadratic up here. So therefore 0.3x, so actually I should say the point of intersection, if there is one, will be where 0.3x take 6 equals a half x squared take 3x. And then we have a quadratic we can solve for x. So subtract that 0.3x from the right hand side, add the 6, we would get half x squared take 3.3x plus 6 equal to 0, and multiply through by 2 just to neaten it up a little bit. So x squared takes 6.6x plus 12 is equal to 0. You don't have to do that. And then remember, we can use the discriminant to determine how many points of intersection there are, if there are any. So the b squared take 4ac, let's find out what that equals. B squared is negative 6.6 squared take 4 multiplied by 1 multiplied by 12. This looks like it's going to be negative. This looks like it's going to be larger than this number, but we can just put that straight into a calculator and c. So we've got negative 6.6 squared take 48, and I get negative 4.44. And remember what that means if the discriminant is less than 0. So therefore b squared take 4ac is less than 0. That means there are no points of intersection. So therefore no points of intersection. So that means this diagram was pretty accurate. The swimmer dived and she did not hit the bottom of the pool. The straight line of the bottom of the pool does not intersect with the quadratic of her dive, so she's safe. She did not get brain damage, which is great. Alright, so that was just finishing off that section on simultaneous equations of graphs. I would just say that these are the types of questions you should worry about. You will not be expected, as we did the other day, to sketch a quadratic and a straight line and find solutions that way, because you can always do it algebraically. So these are the types of questions that are more relevant. Okie doke. We've done linear inequalities. Now on to quadratic inequalities. Okay, section 3.5. Quadratic inequalities. Hello, hello. Oops. That's meant to be a box. Okay. Quadratic inequality says to solve a quadratic inequality, rearrange so that the right-hand side of the inequality is 0. Solve the corresponding quadratic equation to find the critical values. Sketch the graph of the quadratic function. Use your sketch to find the required set of values. The sketch shows the graph of f of x equal to x squared take 4x take 5, factorized to x plus 1x take 5. The solution to f of x equal to 0 are x equal to negative 1 and 5. Okay, we've already done that. These are called the critical values, where the graph cuts the x-axis. Hello, hello. The solution to the quadratic inequality, f of x greater than 0, are the x values when the curve is above the x-axis, the darker part of the curve. This is when x is less than negative 1 over here, or when x is greater than 5. The set notation is this. We looked at that in the previous session. We talked about this set notation in detail. The solutions to the quadratic inequality x squared take 4x take 5 less than 0 are the x values when the curve is below the x-axis, the lighter part of the curve. This is when x is greater than negative 1 and less than 5. So we would write it as this, with those x between negative 1 and 5 basically. In set notation it is x colon negative 5, x between negative 5 and 5. Again, we talked about that previously. Okie doke. Here's another example. Basically the same as what we just talked about. And another one, what's this one saying? So find the set of values for which find the set of values of x for which 12 plus 4x is greater than x squared. Okay, hence find the set of values for which 12 plus 4x greater than x squared and 5x take 3 is greater than 2. Okay, so you can have a combination of linear and quadratic equations as well. You just basically include that in your set of solutions. Here it says you can use a table to check your solution. Okay, So this is like, I would suggest either graphing it or doing the table. Well, I guess also it is, as they say, you can use it to check that your graph is correct. So basically what this is saying is, if the graph looks like this, you should get a negative value for x between -2 and 6. So if you plug in, say, 0 for x, you should get a negative solution. If you plug in 7 for x, you should get a positive solution. And if you didn't, maybe you know that your graph is wrong. So anyways, you can see here with the linear equation, they drew a number line here, and they have the set of values for the quadratic and the set of values for the linear equation. And you want where the two sets of values overlap is 1 to 6 in here. And here it says a little hint. This question is easier if you represent the information in more than one way. Use a sketch graph to solve the quadratic inequality, and use a number line to combine it with the linear inequality. Okay, nice tip there. Another example. Find the set of values for which 6 on x is greater than 2. That's interesting. Might just write this example down. So if you're looking at this inequality, you might think just to multiply by x. So you'd have 6 greater than 2x. But what this is saying is, well, we don't know if x is negative. So we would actually get two separate inequalities from this. If it's positive, then we get 6 greater than 2x. But if it is negative, then we actually get 6 less than 2x, because we have to flip that inequality around. They've done it slightly differently. They have turned it into a quadratic by multiplying. What have they done? Instead, multiply both sides by x squared. Okay, so instead of doing this, you can also multiply everything by x squared. Yeah. Although I don't see a problem with doing it this way, that you can just say, you can have one solution which is greater than, one solution which is less than. But yeah, exactly. Multiply by x squared means you're definitely multiplying by a positive. You have the same inequalities. So if we multiply by x squared, we get 6x greater than 2x squared, as they do here. And then they solve that quadratic. Okay, so that's an important thing to remember. We cannot just multiply by an x. We need to consider that x might be negative. All right, let's do a couple of these early questions. So for exercise 3E, let's just do A and B. So we've got x squared, take 11x plus 24 greater than 0. Usually the way that I write these is I say the critical values are given when x squared take 11x plus 24 is equal to 0. Then I solve that quadratic. This can be factorized. Factors of 24 that make 11, 8 and 3. So this could be factorized to x take 3 and x take 8. So the solutions are x equal to 3 or x equal to 8. So again, they're my critical values. We can draw a quick sketch. Does not have to be to scale. It does not have to be neat. Just has to give you an indication of what's going on. So this is a positive quadratic, so it's going to be this way. And we want it when this quadratic is less than 0, so when it's down here, below the x-axis. Hello. Would this apply to the CIE syllabus? What's the CIE syllabus? Sorry for my ignorance. I apologize. So again, when it's less than 0, therefore if we drew a number line, now I don't always draw a number line, but it can help when you're first starting this, on this. When it's less than 0, it's between 3 and 8, and we want empty circles because it's not equal to those things, it's only less than or equals to. So that would be my solution set there. Hello. Chess, not often. I like watching it though. It can be entertaining to watch, but I don't often play it. It's quite a difficult game. So let's try to use the set notation as well here. So we can say the solution set is x between 3 and 8. Okay. For B, we have 12 take, I might write this around the other way, so I'm doing B here, but I'm going to write it as negative x squared take x plus 12 greater than 0. And I always find it confusing when there's a negative quadratic of x squared. I never found out what the CIE syllabus is. I might look that up later. If I divide through by a negative here, this actually has to be less than 0 now. And factors of 12 that make 1, 3 and 4. So I can factorize this to, oh, I forgot to, so next step, sorry. So once I've done that, the next step is to say the critical values are when this quadratic is equal to 0, and I can straight away factorize it to negative 4 and positive 3. That will give positive 1 and, sorry, positive 4 and negative 3. That will give positive 1 and negative 12. Oh, international. So international GCSEs or international A levels. Yeah, for sure this would apply. I believe most of the content is pretty similar. Oh wow, cool. Yeah, for sure. If you have any past papers, I'm sure they'd look fairly similar to the AS papers. So then the critical values are x equal to negative 4 and x equal to 3. And then draw your quick sketch. So we've got negative 4 and 3. And it's a negative quadratic at the start, although this one is a positive. So I've actually switched it around to be a positive quadratic, just to confuse you all. If you're solving this one, remember to draw it around the other way. But you can see, even if you drew it that way, we'd still be looking for the same section between -4 and 3. So now I can say my solution set is x between -4 and 3. Okay. So that's my general approach to quadratic inequalities. Let's move on to some different questions. I feel like I missed something, but yeah, no. Okay. Question 2, let's see. It says find the set of values for x for which these inequalities exist. Okay, so these are just slightly different, adding a little bit more complication to it. Let's do C here. So we've got x multiplied by 3, take 2x greater than 1. And basically just simplify until you have a quadratic on the left and 0 on the right hand side. So this would be 3x take 2x squared greater than 1, expanding those brackets out. And then -2x squared plus 3x take 1 greater than 0. And now let's go ahead and see if we can factorize this. Factors of -1 and -2 that make +3. So the only factors of -2, well, let's just do 2 and 1, and 1 and 1. And which one has to be negative? That's my only question. You can see I always get confused when there's a negative there. I don't know why. Oh yeah, so if both of these are negative, can we factorize? That would be 2 plus 1. Of course we can. I was thinking it would be 4 for some reason. So we've got -2x and x. And that negative needs to be multiplied by -1 and then +1. This will expand to -2x squared plus 3x take 1. Okay, and then the critical values are x equal to a half or x equal to 1. Draw a little sketch. Got one critical value at a half, 1 at 1, and this is a negative quadratic, so it's upside down or a frowny face quadratic, and we want it when it is greater than 0. That's this part in here, right? This is 0, right? That's what that line represents. When it's greater than 0, it's between a half and 1. So the solution set then is x between a half and 1. Let's go ahead and check these before I move on. Just make sure I'm not making any mistakes. So this was exercise 3E. And if you want to go back at any stage and do the remaining questions for extra revision, if you feel like you need it, then I would think that would be a great idea. So we did 1A, Okay, they're not writing it with set notation, but well, it's still x between 3 and 8. B was between -4 and 3. And then we did 2C was between 1/2 and 1. Okay. All right, on to the next set of questions. Let's have a look. It says use set notation to describe the set of values for x for which the quadratic and the linear equation. So basically we have two inequalities here. I'll do one of these. Okay, C looks interesting somehow because we have some brackets in there. So let's do C. C, we have 4x squared take 3x take 1 less than 0. And 4 multiplied by x plus 2 is less than 15 take x plus 7. Okay, just fits on. So again, basically we solve both of these. We get two sets of inequalities, and the solution is the inequality that fits both. So for this one, the quadratic on the left, actually let's leave that until second. Let's do this one first. Here we have 4x plus 8 less than 15 take x take 7. And then bringing everything over to the left hand side, we have 5x, 4x plus x, and then 15 take 7 is 8. 8 take 8 is 0, so all we'll have there actually is 5x less than 0. So then x is less than 0. Okay. Now let's deal with the quadratic. Remember, we find our critical values. So we'd say this is when 4x squared take 3x take 1 equals 0. And can we factorize? Factors of 4 and 1 that make -3. 4, so we could do 4 and 1. -1 -1, and then +1. That should give me -3 and -1 on the end. Yep. So then my critical values are x equal to -1 on 4. Or x equal to 1. Do a quick sketch. So -1/4 and 1 on my axis here. And this is a positive quadratic, so it goes like this. And we want it when this quadratic is less than 0, so it's in here. So for this inequality, we have, actually let's draw our number line now. So next step when you have two inequalities is to draw the number line and combine them. So for this one, we were talking about x less than 0. So this is 0 here. So that would represent that inequality. And for this one, we had some values at -1/4 And this number line doesn't have to be to scale, by the way. Just to show you kind of, it's just to help you with your solution. This one was between -1/4 and 1, and your solution set needs to satisfy both of these. So my solution set here will be between -1/4 and 0 in this section here. Hello, hello. Because that's the section that fits into both. Importantly, because they say "and" in the question, so you need to consider both inequalities. Okay. From India. Cool, cool. Welcome. People from all around the world today. That's cool to see. What's the time in India at the moment? Question 4 is a problem-solving question. So it says, given that x is not equal to 0, find the set of values of x for which 2 on x is less than 1. Okay, so we talked about examples like this. Let's do A and then F. F looks interesting as well. Oops. So the reason they say x is not equal to 0 is because then that would be undefined. So x cannot equal 0 in this case. Oh, only 630. Okay. Pretty similar. And remember, we talked about this just before. We cannot just multiply both sides by x here because x might be a negative. So what we do is we multiply both sides by x squared, guaranteeing that we multiply by a positive number, and then we don't have to worry about the inequality sign. So if we multiply by x squared, we get 2x less than x squared, and then x squared take 2x is greater than 0. And then the critical values are when x squared takes 2x is equal to 0. So factorize the x. We get x equal to 0 or x equal to 2. And then draw a little sketch. You don't have to do this every time. If you feel confident writing the solution set without the sketch, then possibly you can skip this step, but I would suggest doing it just to avoid any errors. So this is a positive quadratic, so it's up this way. Smiley face. And we're looking for the values of x greater than 0. So that's these sections in here above the axis. Okay, so then the solution set is x less than 0, right? Over here is less than 0, and or x greater than 2. Okay, so remember that union symbol means or, so x could be less than 0 or x could be greater than 2. Okay, let's have a go at F now. As always, I leave questions for you to do by yourself if you want that extra revision at some point. Okay, what can we do here? Again, we can multiply by x squared because that's always going to be a positive. The exams, I have no idea when the exams are in India, but in the UK, it depends. It's a bit of a mess this year because of what happened, but there are resit exams in September for A levels. Otherwise, generally exams are in June. Okay, so for this one, we could still multiply through by x squared. It looks a bit different, but we're still essentially following the same steps. Oh, October, November. Yeah, sorry, October. They're a little bit... No, that's right, I was getting confused. They're later than the GCSE ones, aren't they? Anyways, multiplying through by x squared, we get 6 plus 7x less than or equal to 3x squared. And then bring everything onto the same side. We will have 3x squared take 7x take 6 less, whoops, almost made a critical error there, greater than 0, because I brought everything over here. So just notice the direction of the inequality signs. Try not to make mistakes there. It's easy to mess up. Then critical values. Are when 3x squared takes 7x takes 6 is equal to 0. Can we factorize factors of 6 and 3 to make 7? Well, the only factors of 3 are 3 and 1. And if we multiply 3 by 3 and 1 by 2, we should be able to make 7. So this would have to be a negative 3 and a positive 2, and we'll be able to factorize. So this is going to be 3x and negative 3 and plus 2. That should expand out to 3x squared take 7x take 6. So then my critical values are negative 2 on 3 or 3. Draw a little sketch. Negative 2 on 3 and 3 are my critical values, and this is a positive quadratic again, so it's up this way. Open to the sky. And we want this when it's greater than or equal to 0, so it's going to be these sections here. So the solution set is when x is less than or equal to negative 2 on 3. Remember, whatever inequality is in the original problem, we use in the solution. And x less than or equal to negative 2 on 3, or x greater than, running out of room, x greater than or equal to 3. Okay, hopefully you can still see that squished in there. Okay. I think I have time for a couple more. Might have to finish this off at another point. So question 5 says find the range of values of k for which the equation x squared take kx plus k plus 3 equals 0 has no real roots. And then part B says find the range of values of p for which the roots of the equation px squared plus px take 2 equals 0 are real. Okay, fairly standard stuff here. So we're going to use the discriminant here. Remember the discriminant is b squared take 4ac, and when it has no real roots, this will be less than 0. So that's what the question is telling us. Assume that the discriminant is less than 0. So b squared, sorry, b is negative k, so this is negative k squared, take 4 times 1 times k plus 3, less than 0. And then this is going to give us a range of values for k. So k squared, sorry, negative k squared is just k squared, take 4k, take 12, less than 0. And here we have a quadratic that we can find the values of k. And factors of 12 that make 4 are 6 and 2. So this could factorize to k take 6 and k plus 2, less than 0. So the critical values are k equal to 6 or k equal to negative 2. And then draw your quick sketch. And it's a positive, so it'll be this way. And we want the values of k less than 0, so the range of values for k will be between negative 2 and 6. And that's your answer there. So range of values for k between negative 2 and 6. Part B, if there's something that's not quite making sense, feel free to just point it out. Okay, so let's go over this one again. Basically, you're given a quadratic with some unknown in it, k, and k could be anything, right? But they give you a condition. They say this quadratic has no real roots. This means that the discriminant b squared take 4ac is less than 0. We talked about the discriminant in the previous session. If you missed that section on the discriminant, you might want to go back and check that, because we talked all about the 3 situations. The discriminant could be less than 0, equal to 0, or greater than 0. So you might want to check that section on the discriminant if you're not sure what's going on. Then we say if it has no real roots, the discriminant is less than 0, and we plug the b and the a and the c in, and we get a range of values for k. Okay. Part B says they give us a quadratic px squared plus px take 2 equal to 0. Now we want the range of values for p for which the equation has real roots. So this is the situation where the discriminant is greater than 0. Okay, just to compare, this was when it had no solutions. This is when it has 2 real solutions, greater than 0. So here b is p, so we'll have p squared take 4 times p times negative 2 greater than 0. So p squared plus 8p is greater than 0. So then factorize. We've got p multiplied by p plus 8 greater than 0. So my critical values are p equal to 0 and p equal to negative 8. It's a positive, so it's up this way. And we want it when it's greater than 0. So the values of p greater than 0 are when, this graph is greater than 0 when p is less than 0 or greater than negative 8. Sorry, I've drawn those around the other way. The negative 8, of course, should be over here. Negative 8 is less than 0. Okay, so then the range of values is p between negative 8 and 0. All right, let's go ahead and check what we've done so far. Starting with 3c. What was it up to? 5. Sorry, 3c. (3c) was x between negative a quarter and 0. Cool. 4a was x less than 0 and x greater than 2. Okay, they haven't used that notation, but still the same answers. 4f was x less than or equal to negative 2 and 3 and x greater than or equal to 3. And 5a was k between negative 2 and 6 and b, yeah, I said one thing and wrote down another thing. So remember I was saying that it was less than negative 8. And also I got something, so I made 2 errors in this problem. This should be greater than or equal to 0 because the discriminant can be equal to 0 and have one solution. Okay. Lucky I checked that one. So this is when p is less than or equal to negative 8 or p greater than or equal to 0. Okay, couple of errors there, but it's all fine. Okie dokie. Might have to finish those off next time. And then, so tomorrow we'll be moving on to inequalities on graphs and finishing off chapter 3. If anyone has any other questions, feel free to ask them. I'll be heading off in about 5 minutes. Otherwise, thank you for tuning in today, and I hope to see you tomorrow at around 11 AM London time, hopefully, although sometimes I start later than that. How can I differentiate between statistically independent events and mutually exclusive events? Independent. So independent is when the events do not impact each other. Like a coin toss. E.g., coin toss, dice roll. Mutually exclusive. This is when things cannot happen at the same time. So this is like raining and not raining. It can't be both raining and not raining, it has to be one or the other. So if we compare them, I guess the thing is that independent can either be mutually exclusive or not. So it can be mutually exclusive. Sorry, if it's mutually exclusive, it must be independent. No, that's not true. Actually, there's no connection there, is it? So, I mean, basically, if it's raining, that determines if it's not raining. So, to answer the question, how can you differentiate between them? I would just say they're two separate ideas. So, independent is talking about the influence of one event on another. So let's try to think of something that's not independent. Well, if the temperature and how cloudy it is. temperature and cloud cover. They would be dependent because the cloud cover impacts on how hot or cold it is. Dependent. So if it's cloudy, you can assume it will probably be cooler than if it was not cloudy. Whereas if they're independent, if you toss a heads, you can't say what the next one will be based on what you just flipped. And then mutually exclusive, that's kind of a separate idea, really, as far as I think about it. Like, it's just saying that if this happens, something else cannot happen. Okay, so we have a question. So PQ is equal to 0.2, PR is equal to 0.4. Oh. The complement of Q intersect R is equal to 0.4. What is the relationship between Q and R? I see. So is it independent or mutually exclusive? Is that the idea? Yeah, so this is saying the probability of not Q intersect R is 0.4. This is equal to PR. So we can say the probability of complement of Q intersect R is equal to the probability of R. Therefore, I'm thinking that they are mutually exclusive. I don't know if you have the answer or not. That would be my answer. So Q complement is everything outside of Q. If the intersection of Q complement and R is just R, then there must be no intersection. So let me put it another way. If there was some intersection, this is, by the way, this Venn diagram represents not mutually exclusive, because there's some intersection where both things can happen, right? In here, this is where we have P of Q and R. So this Venn diagram represents not mutually exclusive. And this area over here represents P, the probability of Q complement. This is probability of the complement of Q. Or you could just say the complement of Q. That's if this is set Q, this is set R. Sorry, I should just say that's the complement of Q. So if the complement of Q equals R, actually let's do it the other way. You can see from this diagram the complement of Q is clearly less than the set of R, right? This orange space is less than the orange plus the yellow, which is the entire set of R. So at the moment, when they're not mutually exclusive, the complement of Q is less than R. If we say then that the complement of Q is equal to R, which we had up here, then that means that they must be like this. They must be separate. So this set then is both R and the complement of Q over here. At least that's how I would think about it. So if events are independent, they can still intersect. So remember we talked about these independent events. Now these are not good examples of those. Let's try to think of two independent events that would also have an intersection. Well, I mean, I guess anything really. Two events that are independent that also can happen at the same time. Well, you could say, okay, let's try to think of a different example. Okay, let's say it could be raining and what else? Liverpool is playing. Yeah, that's a classic one. Temperature and number of ice creams sold. Although that would be, I would argue that's dependent, because the temperature impacts on the number of ice creams sold. So this one, it could be raining, right, at any point, and Liverpool can be playing at any point, and sometimes we'll have the situation where it's raining and Liverpool are playing soccer, football. And the fact that it's raining does not impact on whether they play football or not, unless you know, unless they're really soft and they say, "Oh no, it's raining, we don't want to play football." But you get the point. Even Liverpool play in the rain. So yeah, and also the fact that they're playing football does not impact on if it's going to rain or not. So these are examples of two independent events that also have an intersection. They can also happen at the same time. Now, you could also say you could also have another example. What's going on in the league right now? I don't even know. Wow, Liverpool are on top, 96 points. All right. Nice. Then you could have another situation where you have Liverpool playing and Norwich winning. These are mutually exclusive because you cannot have sorry, I should say playing Norwich and Norwich winning. You cannot have Norwich beating Liverpool, so these are mutually exclusive. Nice. Okay. Hopefully that helps a little bit. I've got to go. So thank you so much for tuning in. And if you want to tune in tomorrow, I'll try my best to start at 11 AM London time. Okay. Bye for now.